Good morning to all of you. Am I audible?
Yes, sir.
Thank you. So today we would be continue the unit number 6. In the last lecture, we have learned about the digital to analog converter and the two types of DAC. We have learned binary weighted digital to analog converter as well as the R2R ladder digital to analog converter. Now today we would be see some specifications about the digital to analog converter and then uh, analog to digital converter. So first of all, the first specification that I have pointed out here, resolution. So what is resolution? Basically, it is defined as the smallest change that can occur in the analog output voltage as a result of change in digital input. What is resolution? It is smallest change that can occur in the analog output voltage, because here output is analog, as a result of a change in digital input. So simply, if you have to be see, resolution is nothing but the value of the LSB or the weight of the least significant bit, and you can define the resolution in terms of voltage like uh, full scale voltage range, output full scale voltage range upon 2 raised to the power n minus 1, and n is here the number of bits. So you can see here there is a one table I have also shown that would be show you that what is the effect of the number of bits on the resolution when you have to be going to calculate the resolution. For example, if you have taken the 6 bits, means 2 raised to power 6 minus 1, that is 63 intervals are there, and the size of the LSB would be, in that case, if you have taken full scale output voltage as 10 volt, it would become as 158.8 millivolt. So this is the resolution of the DAC having the 10 volt full scale voltage, and in terms of percentage of full scale, it would be 1.588%. Similarly, as you increase the number of bits, uh, the size of the LSB would be decreases, okay, and the resolution is more better. Second specification, if you have to be think, that is accuracy. So here we have to talk about absolute accuracy. So absolute accuracy is the maximum deviation between the actual converter output and ideal converter output. And accuracy is also given in terms of LSB increments or percentage of full scale voltage. The third specification is linearity. So it is the measure of linearity between binary input and analog output. So the linearity of digital to analog converter is defined as the precision with which the digital input is converted into the analog output. And generally there is a one term very frequently used, that is a linearity error in the case of a specification of digital to analog converter. The fourth specification you have to see, this is settling time. So this is the time required for the output of digital to analog converter to settle within the plus minus 0.5 LSB or 1/2 LSB of the final value of the digital input, that is between 0 to full scale voltage. So generally in the DAC there is a maximum error could be possible is plus minus 1/2 LSB. So whatever the time required for the output of DAC to settle within that particular range of final value of digital input, that is amount of time is called the settling time. Means after this the output would be remains stable. Fifth one is monotonicity. So if you have to talk about the digital to analog converter, it would be stated as monotonic if analog output increases for an increase in the digital input. A monotonic characteristics is essential in generally for the control applications, because if digital to analog converter would be not maintain the monotonicity, so it would be lead to the oscillations. So the last one is, if you have to talk about this characteristics of the DAC, that is stability. So the stability, the ability of the digital to analog converter to produce as a stable output all the time is called the stability. Means the performance of the converter changes. Generally, we know the performance of the converter would be changed with the change in or with the drift in the temperature, aging effect, or power supply variations. If your digital to analog converter would be produce the stable output with respect to the variation in these terms like temperature, power supply variation, so it is called the stable digital to analog converter. And all these parameters that we have learned, this means offset, gain, linearity error, monotonicity may change from the values specified in the data sheet. And generally the temperature sensitivity in the case of digital to analog converter, it would be define the stability of the digital to analog converters. So these are the some characteristics that also you have to be know along with the types and as whatever the description we have learned about the digital to analog converter. I have only described here only the definitions. For the detail, you can refer the books where some graphs are also shown that would be support the definitions and justify the statements that I have taken in this lecture. Now we have to be moved for the from digital to analog converter to analog to digital converter, ADC. So this is basic or general block diagram of the analog to digital converter. So what is basically a analog to digital converter? Analog to digital converter converts an analog signal into the digital signal, and the digital signal with a binary code. Generally, digital signal is represented with a binary code, and that is we know that binary is a combination of bits 0 and 1. So here in this slide we have shown the general block diagram of A to D or analog to digital converter. You can note it down. So you can see here we have applied the analog voltage here to the first block, that is pre-filter. Okay, and then the output of the pre-filter is anti-aliasing filters are used here. So the output of this would be given to the sample and hold circuit, and the output of sample and hold circuit is given to the quantizer and finally to the encoder. So what basically happens in this case, if you have to see the block diagram, the pre-filter, it would be avoid the aliasing of the signal at the generally high frequency signals. It would be prevent the high frequency signal from the overlapping during the sampling. And then the output of this pre-filter is fed to the sample and hold circuit. Sample and hold circuit will be hold the input analog signal into analog to digital converter at a constant value during the conversion time. And the third block is quantizer. The quantizer basically segments the reference voltage signal into some step size or the sub ranges. Typically, for n bit digital output, A to D converter having a 2 raised to the power n sub ranges. And the digital processor, this is the last one, the digital processor or the encoder, you can say. A digital processor forms the encoder circuit which encodes the sub ranges or the steps of output of the quantizer into the corresponding digital bits. Therefore, input signal is converted into the equivalent digital output code within conversion time. So I hope it is clear that description of the block diagram of A to D converter. Now we have to see the types of ADC. There are the various types of ADCs are available, and you can categorize the ADC in different respects, like program, non-program type, closed loop, open loop type A to D converter, direct A to D converter, and the integrating type A to D converter. There's a various way that you can classify the A to D converter. But as per syllabus, we have to learn the three types. That is, first one is flash type, second is dual slope, and third one is successive approximation A to D converter. So we start with the first type of the A to D converter, that is flash type A to D converter. Its another name is simultaneous type A to D converter. And basically, you can say it would be came under the category of the direct type A to D converter. So a flash type A to D converter is basically based on the principle of comparing an analog input voltage with a set of reference voltages. To convert analog input voltage into a digital signal of n bit output, 2 raised to the power n minus 1 comparators are required. So to convert analog input voltage into the digital set signal of the n bit output, we have to be required the 2 raised to the power n minus 1 comparators. Okay. So for example, if you are going to implement the 2-bit flash type A to D converter, you have to be required 3 comparators. If you have to going to implement 3-bit A to D converter, you have to require 7 comparators. So this is the basic block diagram of the 2-bit flash type or simultaneous type A to D converter. Please note down the diagram that we have also implemented in the practical session as well. So you can see here, it is, if you have to see the block diagram of this 2-bit A to D converter, there is a, as per the phenomena of 2 raised to power n minus 1, means here we have to be required 3 comparators. So you can see in the diagram, 3 comparators are shown, C1, C2 and C3. And the non-inverting terminal input of all these comparators is connected to the unknown analog input voltage, that is Vi. And inverting terminals are connected through the supply voltage, and the supply voltage has been distributed along with these 3 comparators, that is separated from each other with the respect to the resistor R. All the resistors having the same value, so there are the 4 resistors are used in between the maximum voltage plus V to ground signal. And you can see then when you have to arrange in this such a way the comparator inputs. So each comparator, if you have to be start from the ground level to the maximum, move through towards from ground to maximum positive voltage, you would be found that the first comparator having the non-inverted terminal voltage is V upon 4, then there is a 2V upon 4, then 3V upon 4, like this, and then finally the V is there. Okay, so this V has been be divided by these three comparators into the equivalent of V upon 4 terms. Now the output of this comparator is given to the XNOR gate. The output of the comparator C2 and C3 is given directly to the XNOR gate input, and the comparator C1 and C2 output is given to the AND gate input. And then further the XNOR gate output is given to another AND gate. Second input to this AND gate is coming from the input of the first AND gate. So in this way, we have to be convert or generate the 2-bit output, that is, one is the B2 is here MSB and B1 is LSB. Now, if you have to be see the description of this 2-bit flash type A to D converter, you would be found that as the inverting input terminal of op-amps are connected to the set of reference voltage V upon 4, 2V upon 4, 3V upon 4, that is coming from the resistive dividing network of the power supply plus V. So the output of this comparator is in positive saturation state when the voltage at non-inverting input terminal is more than the voltage at inverting terminal, because if the non-inverting terminal voltage is more positive than as compared to inverting terminal voltage, your output would be positive saturation voltage. But if opposite case, means inverting terminal voltage is more than the non-inverting terminal voltage, then the output voltage would be switched to the negative saturation state. So depending upon, as it is a comparator, so depending upon the input voltage of inverting and non-inverting terminal, the output of comparator would be switching between positive saturation state to the negative saturation state. So we have to take one case like when analog input voltage is less than V upon 4. We are starting from the ground level and moving towards the maximum positive voltage, reference voltage. So when the analog input voltage Vi is less than V upon 4, the voltage at the non-inverting terminal of these three comparator is less than their respective inverting voltages. That means, hence, in this condition, the comparator output C1, C2 and C3 would be 0, 0, 0. But when the analog input voltage would be increased and reached in between V upon 4 to V upon 2, so what happens? The first comparator C1 would be turned on, or the output would be positive saturation, and rest of the two comparator would be still in the 0, 0. So here output would be 1, 0, 0. Like similarly, when the voltage would be reached to the V upon 2 to 3V upon 4, then C1 and C2 both are having the positive saturation and C3 has the negative. So 1, 1, 0. So this all possible cases has been be represented through this table. You can take the screenshot of this table as well. So this table would be describe you the comparator outputs for the different ranges of analog input voltage and their corresponding digital output voltage. So if you have to be see the first case we have already discussed, the Vi in between the 0 to V by 4, all three comparators 0, 0, so output would be 0, 0. But in the second case, when Vi is in between V by 4 upon C1 is also positive saturation and C2, C3 would be 0, 0 because negative saturation state. So B1 that is LSB would be now 1 and MSB would be remains at the 0. In the third case, when input voltage in between V by 2 to 3V by 4, so the comparator outputs C1 and C2 is 1 1 because both are in the positive saturation, and C3 is still in the negative saturation, so it would be 0. So 1 1 0. In this case, the possible output would be 1 0. And final case, when the input voltage is in between 3 by V by 4 upon 2 V, so it would be all three comparators would be now goes into the positive saturation state, that is 1 1 1, and digital output would be also 1 1. So in this way, your analog to digital conversion would be performed in the case of 2-bit flash type A to D converter. And you can also derive the logic expression from this table for MSB and LSB, B2 and B1 respectively. So B2 would be, you can see from the table or refer the table, it would be C1 C2 complement of C3 plus C1 C2 C3. So there are the two states where the B2 would be 1. So it would be written as C1 and C2. And then B1 is having C1 C2 C3 complement and then C1 C2 C3. So finally the equation for the B1 would be C1 into C2 X naught C3. Okay. So in this way you can derive the equation mathematically also with the help of Boolean equation, and that would be helpful for also writing the table as well. Now in a similar fashion you can derive or explain the 3-bit flash type A to D converter. But here how many comparators will be required? Now the number of bits is increased, so we have to require the 7 comparators. In the first case we required only 3 comparators. Now the number of comparators would be doubled. When you have to be only increase 1 bit, the number of comparators would be doubled. So in this, please note down this diagram. This is the block diagram of a 3-bit simultaneous type or flash type A to D converter, where you can see that there is a 7 comparators has been be shown, and the voltage, non-inverting input voltage has been be connected to the again the analog input voltage Vi, and the inverting input voltage is connected to a set of reference voltages V upon 8, 2V upon 8, 3V upon 8 up to the 7V upon 8 through the resistive voltage divider network. Okay. So in a similar fashion we have to be here increase V by 8, 2 by V by 8 like up to the 7V by 8 up to the reference voltage V. And you can see that output of this 7 comparator is passed through some coding circuit, because it is very difficult to represent the structure of the gate based structure. You can use it, but it would be make the circuit complex. So we have to be use here coding circuit. Generally we use a parity encoder, and then finally we have to be get a 3-bit digital output. Okay. So I hope all of you have noted down this diagram. Now we have to be explain this 3-bit flash type A to D converter with the help of this table. Here you can see that in the leftmost column we have written as the analog input voltage range, then the comparator output from C1 to C7, and then finally the digital output B3 to B1. Okay. So you can see here, as in the previous case, initially when the input voltage is less than V by 8, so all the comparator would be at the negative saturation state, 0 0 0 0 would be there, and digital output is also here 0 0 0. But as you increase the input voltage by each resistor dividing network, so one by one your comparator would be goes into the positive saturation state. So initially in the first case, when input voltage is V upon 8 to 2V upon 8, so C1 would be 1 and rest of would be 0 0. So finally V1 would be 1 and V3 and V2 is 0 0. So in every increment of the voltage or we would be go from one range to the second range, your one more comparator would be activated. Okay, and in this way your digital output would be also changed according to the combinations. So this is the final structure of this particular 3-bit flash type A to D converter, and this is a reference table to defining the comparator outputs as well as the digital outputs. Okay, so note it down please. And we would be see the practical circuit also. Here we have to be take one of the IC, that is IC 74148, that is nothing but a 8:3 priority encoder that is used to implement this 3-bit A to D converter. So from this table we have to be see that the logic expression for the V3, V2, V1, that is digital output, are complex due to their dependence on the 7 input variables C1 to C7. Hence the coding circuit is implemented using a priority encoder. And here we have taken the example of the priority encoder of IC 74148. It is simply a 8:3 priority encoder with active low input and outputs. So since the comparator output is active high generally, so and the priority encoder is active low, so to matching between both of them, what we have done, we have connected to the inputs of the encoder through a inverters, so that the output of encoders are inverted once again and get active high digital outputs V3, V2 and V1. So you can see here the diagram, this is the logic diagram for the 3-bit simultaneous type A to D converter. Up to this converter section, the connection is same as we have referred in the previous diagram, but as the output of this comparator is active high, and this is 8:3 priority encoder that is having the low inputs, it accepts only the low inputs. So what we have done here, we have connected the output of each comparator as an inverter, one inverter. So in this way, all 8 inputs of this priority encoder would be receive a active low input, and then the output, it would be invert then this active low input the active high inputs, and that would be appeared at the output as a digital output through the V3, V2 and V1. Okay. So please note it down this diagram also, take the screenshot of this. So this is about the 3-bit flash type A to D converter using IC 74148, 8:3 priority encoder. Now if you have to see the advantage of A to D converter here, so there are some advantage, like simultaneous type A to D converter is the fastest because analog to digital conversion is performed simultaneously through a set of comparators. Hence it is also called as a flash type A to D converter. Its conversion time is nearly 100 nanosecond or less. Okay. And the second advantage is the construction is simple and easier to design, but it is also one disadvantage, that is the simultaneous type A to D converter is not suitable for analog to digital conversion with more than 3 or 4 digital output bits, because the fact that 2 raised to the power n minus 1 comparators are required for an n-bit A to D conversion. So what happens, number of comparators required would be doubles for each added bit. That's why it is not suitable for the higher digital output bits. Okay. Now goes to the second type of the analog to digital converter, that is dual flow A to D converter. This is the second one that we have to learn here. In the dual type A to D slope type ADC, the integrator generates two different ramps, one with the unknown analog input voltage Vi and as the input, and another with the known reference voltage minus Vr. Hence, it is called the dual slope analog to digital converters. And the operation of the dual slope A to D converter could be explained with the help of this diagram. You can see here, this is the, please note down this logic diagram of dual slope A to D converter. Everyone please note it down. All of you has noted down this diagram till now. We have to be go through the operation of this dual slope type A to D converter. Here you can see that in the diagram, initially there is a switch is shown that is having this switch would be switching between the two values of the voltage. One is the analog input voltage Vi, another is the reference voltage minus Vr, and the switching operation would be depend upon the output of the control circuit, that is taking the instructions from the count detector for the time t1, and the count detector having the taking the instructions from the 4-digit decade counter. But as per the value of this switching, this is the integrator structure, where you can see that the C is capacitor, is the feedback capacitor here connected to the R in the inverting terminal, and non-inverting terminal is grounded. And the output of this integrator is given to the comparator. In the non-inverting terminal is grounded here, and inverting terminal is the output of the integrator, that is Vs, and the output of this comparator is Vg. Along with this, clock is applied to the AND gate. Okay, and this output of this gate, AND gate, is given to the as a clock signal to the 4-digit decade counter, and the output of this decade counter is detected by this count detector, and that would be given to the control circuit, and the output of the control circuit is used to latching operation, and the latches the 7-segment decoder. That output would be displayed as a digital output. Okay, so if you have to be see here, the operation of dual slope type A to D converter, assume that 4-digit decade counter is initially reset to 0000, and the ramp output Vs is reset. The integrated output is considered as the ramp output here, reset to 0 volt. So analog input voltage is positive, and the input to the ramp generator or integrator is switched to the analog input voltage. So here analog input voltage is considered as a positive. Okay, and the integrator output is nothing but the ramp output, Vs is there. So what happens, since the positive analog input voltage is connected to the inverting terminal of the integrator, and while so it would produce a negative ramp like this, a negative ramp, because it is connected to the inverting terminal of the integrator. Okay, so the integrator output Vs is a negative ramp here, and while the comparator, it would be applied to the comparator, and if you have to be see, this negative ramp is smaller as compared to the non-inverting terminal voltage, that is 0 volt. So what happens, the output of the comparator VT is a positive here, and the positive signal is along with the clock is passed through the AND gate. The output would be high or clock signal. Okay, positive H is there, and this results in counting up the 4-digit decade counter. So count would be increased by the 1 count increased during this time T1. So then count detector would be detect a count, and the this negative ramp would be proceed for the time period of T1. For the time period of T1, that is shown here in this diagram, you can see. So what happens, this negative ramp would be proceed for the time period of T1. This is the fixed time period. And what happens, which would be determined by the count detector for this time period T1. So you can also represent the ramp voltage is defined as minus Vs, because it is a negative, is equal to Vi upon Rc into Ti. Basically here Ti is what? It is T1, you can say, because this is ramp input negative for the time period of T1, and Rc is the time constant of the ramp generator circuit. Similarly, when the counter reaches to the fixed count at time period T1, the count detector gives the signal to the control circuit, which is in turn reset the counter to the 0, and the switches the integrated input to the negative reference voltage. That is a switch that is used in the diagram, you can see. After this, what happens, T1 period, it would be switches to the negative reference voltage minus Vr. That would be generate a positive ramp voltage, you can say, or ramp generator would be begins to increase and upward. It would be increased till it would be not reached to the 0 volt, and during this time, that is the T2, counter get advanced, and when the Vs reaches to the 0 volt, the comparator output would become 0, and the clock is inhibited from the passing through the AND gate, and the conversion cycle is said to be completed because it would be reaches to the 0. In this way, you can see the conversion cycle is completed. So this is the conversion cycle. This is your T1 and this is your T2. So Vs would be here because it is a positive ramp now. So Vi upon Rc into T2, and Vr and Rc are the constant, and time period T2 is variable. Okay. So since the ramp generator starts at 0 volt and decreasing to minus Vs and increasing up to the 0 volt, amplitude of the negative and positive ramp voltage can be equated as follows from this equation. Please start to filling the attendance. Time is only 1 minute is left. So this is the equation. You can say that both are equal. Negative and positive ramp are equal. You can see here the amplitude from this ramp. Please take this diagram screenshot. So this amplitude of Vs would be same for the T1 time and T2 time. So that is shown here. So this mathematical equation. So Vi upon Rc into T1 equal to Vr upon Rc into T2. So it is minus Vi is equal to Vr into T2 upon T1. This is very important relationship. Okay. So tomorrow also there is a lecture of the electronic circuits during the practical session, or maybe in the morning session if any lecture is free. So I stop here. Tomorrow we would be continue from this point. The equation minus Vi is equal to Vr upon T2 upon T1. Okay. Thank you all of you for joining the lecture.